We're going to have 2 long sessions this weekend, and I want to just make sure you understand, what the model is for teaching, or should be. So just me filling you with facts is not going to help you, because you will forget the moment this course is over. So the whole idea is to enable you to be learners on your own. So you have a very powerful free operating system, or you should have access to a very free, very powerful operating system, Linux, that you can do things with after this class is over. You can bring in other robots, you can run other programs on them, including face recognition. You can get a camera on a robot in a simulator to do, face recognition. So all of that is built up from a basic understanding. You can't get there until you first lay a foundation. So that's what we're going to do today. So we might be on this topic. 2 hours was far too short, for another 2 hours. And then we'll take stock before we move on to the next topic, which is kinematics and dynamics and control. All right, so before I go there, I want to make sure that some things were clear. So I skipped the software architecture because this is very temporary. 20.04 is gone, probably this year, and everyone's going to have to move to ROS 2. So what I wanted to focus on is whether you understand the concept of topics. So this is very important. Information about the architecture is not really going to be relevant because it's a new architecture, ROS 2, that's coming up, where you are ahead of me actually, because we had a full 2 days worth of ROS 2. But this part is important to understand what topics is. So when you are trying to find out where the robot is, you typically do it through a process known as odometry. So for that you have to subscribe to the odometry topic. When you're giving commands to the robot to move, you have to do it through a topic, and that topic is /cmd_well. So the key to controlling a robot from any environment, it could be C++, Python, MATLAB, is to know what these topic names are. Well, you don't have to memorize it, but you have to be able to figure out where that information is available. Here's an example of topics, right? We kind of flew through this the other day. So we have 3 nodes, and we don't know what their functionality is, but by now you know enough. There could be an image processing node, there could be 2 image processing nodes, maybe you have 2 cameras on a robot. So imagine if you have 10 robots doing patrol and each one of them has 2 cameras, the number of topics multiplies quite a bit. There might be somebody sitting in a central station, monitoring station, wanting to see what the robots are seeing. Or maybe do some higher level processing of those images, some AI, artificial intelligence based processing. So topics is the way that you get access to those different pieces of data. And each topic has a message structure. An image can't have the same message structure as odometry because number of numbers are different, the transmission rate is different. So this is a data structure created so that you don't have to worry about it. Now, ROS does allow you to create your own new topic and data structure. If you have a special sensor that is so new that nobody has written a driver for it, then you have to do it on your own. But that's a higher level topic, and then again, by Googling, you get an example of how someone else has done it, and you try to copy it and fight your way through all the problems. So the thing to do is to learn how to learn, not necessarily the knowledge, because the knowledge is is fleeting. It goes away after a while. So topics goes with the message structure. Services is the alternate way of getting information. So here is an example of topics. So you have a camera node, which is directly getting information from the camera. So typically this is a driver. All hardware devices have to have some kind of a driver. It's called abstraction in the sense that you don't want the reader to go in and say, okay, what voltage, what current, because they're all mostly electrical engineering devices. You don't want somebody to have to go in and look at the wiring. We used to do that years ago. Maybe back in the 50s and 60s, we had to figure out how a printer was wired to figure out how to use it. So that's all gone now. So this camera node, once it does some basic processing of the image, it publishes it. See, the camera node publishes. It won't be of any use for the camera node to subscribe to anything because it's basically giving out information. So it publishes it, to the bulletin board. I look at it as the bulletin board. It goes and puts something there, and it keeps on doing it with new images. And then the image processing node, which is actually going to do higher level processing, subscribes to it. So all of that has to be set up formally in software. It can't be just make it up. It has to be formal. And then there is another laptop, which obviously is not in the computer. This is the computer on the robot. There's another laptop which just displays the node. Maybe you're sitting at a distance from the robot. You don't want to be running behind it to see the image. So you're sitting in a nicely air-conditioned room and looking at this image display node. You're debugging the navigation algorithms. Maybe the robot is crossing a lane line and you want to know why. So all that is happening in a remote place, on a laptop. So that's the whole idea. This is the architecture of ROS. So this is services, and you can see here that you have a direct request and receive line. So essentially this is timed more because basically you tap the shoulder of a person and say give me an image, and then the person gives an image. So his attention is directly dedicated to serving you. So there is a sense of immediate timing. Topics, no. They go on putting it on a bulletin board. If you miss a few frames, you don't go back and look at the frame that was like 5 minutes in the past, because what use is it when you have a real-time system? You have to worry about the latest piece of data. Maybe later on you can do a postmortem and look at all the images you missed and what you could have done to prevent an accident. But right now you have to process the most recent image. So it's like the data is flying on the bulletin board, and many people can use it or not. They can choose not to use it. And this is exactly how human beings deal with a real-time situation, like driving a car with 2 kids in the back seat and maybe a dog jumping on you. You are focused on the most important thing, which is the scene unfolding in front of you. So the ROS master is no longer there in ROS 2. This was the old architecture of ROS 1. The ROS master, it keeps track of everything, all the topics, messages, how many nodes there are, etc., etc. Yeah, so these are some of the examples of the sophisticated packages that are available. Again, it's software abstraction, because you don't need to, as they say, reinvent the wheel. If already somebody has done it, you can use it. All this is open source software. If you have some special purpose face recognition software, Apple is not going to put it on the internet. So all that, you don't have access to. But anything that is open source is available for you to use. Why would you rewrite the code for that? It's a waste of time. So I showed you an example of our own, my university's efforts in autonomous navigation. We enter a competition every year, and it's actually quite a difficult competition, because imagine, see all the lane lines here look nice because that's gazebo, the simulator. So in the real world, if you use paint lines on grass, and if during the 4 days of the competition somebody cuts the grass, then the lane lines are going to be faded out. Or if it rains overnight, it will wash out some of the paint. So the challenge is much more. In fact, vision is one of the last frontiers, the ability to see and perceive. LiDAR is, in good weather, is more or less 100%. I shouldn't say anything is 100%, but it's more or less certain. The LiDAR can pick up 3D obstacles, but vision is, think about driving on a dark and rainy night. So that's, if the human being can't do it, certainly the camera and the software is not going to do it right now. Who knows with AI what they might achieve in the future. But right now, that is the weak point of software for self-driving cars. It's not able to consistently pick up the lane lines. Look at our lane lines. They are not, it's not as if they paint it every day. It's painted and forgotten for 2 years, and so it's very faded. So that is the challenge. It's a high-level competition which my university won 3 times in a row, and there were some really big schools from the US and Japan and Canada. Even IIT Madras won, I think a couple of years ago. It's surprising because they came all far away, and we got first place. And so we won 3 times in a row in that same competition. Now we have moved on to the self-driving car version of that. The self-driving car, we have a small car which you don't see too much of in the US, because in the US on the freeways, if you drive a car like that, you're risking your life. Very small, tiny thing, and we completely crushed. But in Europe, I've seen it. It's a regular car. It's an electric car that is now being converted into a self-driving car. Okay, and then we'll get to this. I'll walk you through the program again. I ran the robot in a circle. I want to make sure everybody is able to run that program. There were some difficulties in launching ROS. Maybe we'll look into that also. But essentially, here's the background theory, which we will formally derive as the next topic when we take up kinematics and dynamic controls. So, if you have a robot with a forward velocity of 3 meters per second, and then angular velocity of omega radians per second. So, forward velocity and angular rate, right? So, by the way, the actual motors have nothing to do with that. No, they have something to do with that, but they are not directly related. So V is not being driven by one motor, omega is not being driven by one motor. You'll see that in the next topic. But this is also like abstraction. What is the easiest way to drive a vehicle? You press the gas pedal and you turn, right? That's how we drive a car. Anything more would be too complicated for a human being. So if you drive it at V meters per second and turn it at omega radians per second, then we are going to show later in the next topic that it will go on a circle with radius V by omega. So if V is 0.4 meters per second, and if omega is 0.2 radians per second, then you get a circle of radius 2 meters or diameter 4 meters. Okay, so that's the theory that's coming. So the beauty of this is not that you can drive in a circle, because that's pretty much useless after a while. The novelty wears off. But imagine that from moment to moment to moment you change the radius of the circle. So let me ask you this. What is the radius of a straight line?
Infinite.
Huh?
Infinite.
Infinite. What if you spin in place? What is the radius there? If you just spin in place. No, a normal car cannot do that, but differentially steered vehicles can. So what if you spin in place? What is the radius? 0. So between 0 and infinity, there are all these possibilities. All you have to do is figure out the correct ratio of V by omega. And you get all the different radii, which means that between spinning in place and going straight, you can do nice curvatures. All you have to do is change V and omega. If you change V and omega dynamically, then you get beautiful paths, right? And that's exactly how we drive. We drive on little tiny circles. Sometimes you may drive on a quarter of a circle, right? If you're turning into a parking lot, maybe we hold the circle, right? All you have to do is hold your steering wheel and press the gas pedal and you'll be on a circle. But most of the time you want to drive like, if you look at the Formula 1 races, changing direction and lane lines and so on, cutting through between other cars. So it's all little tiny pieces of circles. And of course, in the case of Formula 1, it's all in the driver's head. You and I will not be able to drive like that. But that's why they get so much money. Okay, so any questions on this? All right, so let's fire up ROS. I ran ROS. This is how I run it, by the way. And some of you ran it and the package wasn't there because you are not launching a pneumatic terminal or some such explanation, but I want to make sure that you can run it now. Are you able to run ROS? So as I pointed out, there are a couple of documents posted on Teams. I think they have the word roadmap in the 2 titles. So whatever I did, I'm doing off the document basically. So it's a fallback option in case you don't stay with me. But today we're going to pause now because we need to make sure that you're able to join me here. I was going to try and change the color. Last time it did something strange. Last time meaning a few minutes ago. Oh, great. So it's better to have, for me, maybe not for you, but here, because of the resolution of the projector, if you have a dark background, you can't see the robot there. So maybe I'll talk till it comes up. So you'll always get this error because there needs to be a fixed frame reference. So a fixed frame is a frame that does not move. The robots may move, but this frame cannot move. So you have to pick a fixed frame of reference. Because when different robots are moving and they all carry their own frames, and the camera is on a different frame from the robot, right? The camera could be pointing this way. Also, the camera could be moving around, just like our head. So the frame is moving. It's a very complicated world, and ROS manages all that. So you need one fixed frame as a reference. You can have multiple fixed frames, but you can have only one fixed frame as a reference. So the most important fixed frame is the world frame. But we're not using that as a reference here. I just wanted to mention that this right here, see here, blue, red, and green. So this is buried in the ground at 0, 0, 0. So that is the most important fixed frame. It's called the world frame. Now, if you're doing something with Mars, you can have a frame there also that is fixed, right? But there can only be one absolute world frame. Now, ROS, here, right here, requires a fixed frame. And by default, it goes to the frame of a map. It tries to load a map, and it's not there. So it says there's an error because you haven't defined a fixed frame since there is no map that has been loaded. Now you can load a map. We haven't created a map. So we can't use the map right now, but it's set up to default to the map frame. The frame we typically use, well, again, I'll wait for you to catch up. Have you all fired up ROS? Okay, you go up here. Now, this is open source software. So initially, years ago, I was saying, what is going on here? But later on, you find out that there's a drop-down menu available. If you just click on that row, and we pick ODOM. See, wheel left linked. You can refer everything to a fixed frame, which is the left wheel or the right wheel. It won't make much sense, but maybe you're debugging something and you need it. They give you that option. It won't. Then which robots wheel left link, right? There could be many robots. So these are very specialized frames. You won't use them typically because they are rotating, and you don't want to make that the fixed frame, because if it is rotating, you know what's going to happen? The world is going to be seen from the perspective of that frame being fixed. So then the robot will be spinning. Because if you fix that, then the robot has to spin, right? So they probably have those options for debugging of some kind. I've never used it. So fixed doesn't mean fixed in the sense that it's buried in the ground. It says that's my reference. I'm going to consider that as fixed and everything else with respect to that, right? So that means the world itself will be rotating with respect to that frame. So I've never used it as I said. Now typically you say ODOM, and I'm going to explain what the ODOM frame is right now. So the ODOM frame, we only have one robot, so therefore we only have one ODOM frame. So the ODOM frame is actually where the robot is starting. Right now it's coincident with the world frame. So when you start moving, the ODOM frame will be left behind where this robot was. Similarly, if you had launched another robot here and here, they will have their own ODOM frames. And when they start moving, they will leave behind their ODOM frame. It's a point of reference for odometry of the robot. Is that clear? So the ODOM frame is used as a point of reference for the odometry of the robot, and typically it's a good idea to choose that, particularly if you only have one robot, you choose the ODOM frame. Now, one thing you need to know is, if the robot moves and you don't close out the program, the odometry is cumulative. No, the odom frame is still back there, but the odometry, all the counts, will not go away. If you reset the world, it goes away. If you shut down gazebo and open it again, it will go away. But otherwise, if you just drag it, if you just, robot ends up here and you drag it back to the starting position, it still carries the old odometry count. It is like you walked 100 steps, right? And somebody moved you to a different spot and they say, walk 50 more steps. It'll be 50 more steps over the 100. So it's cumulative. It builds up and builds up unless you reset it. So you'll find a topic which does not seem to be working. It's called reset odometry. So if the robot ends up here and you want to reset odometry, you can. In other words, you're picking up the odom frame and putting it in the new spot. That reset odometry topic is not working for the Turtlebot 3. It works for all other robots, but not for the Turtlebot 3. Maybe it's working in the Ubuntu 22.04 ROS 2 version. Maybe they fixed it. So these are all open source guys. You have to make a request, otherwise they will not do it on their own. They got so many things going on. So, got it? Okay. So now, going back to ROS. So ROS is a spike. It's not the same as gazebo. It's not a simulation environment. It looks like it because you drop the robot identity as yet. I'm going to shortly. So it will look like a simulation screen. It isn't. It is collecting all the sensor data from gazebo and displaying it for your convenience in debugging and so on. You can do the same thing in MATLAB, but I think you're going to have to write your own programs to do the displays. Okay, now, you see here, my add button is missing. I figured out a way around it. So that's being caused by the resolution of the screen. But I found out that if you say show help panel, then the help panel is below the add button, and so it's forced to display the add button. So here it is. For you, it should be okay. So you hit add, and the first thing you need to add is robot model. And there it is. It's not as good as the gazebo CAD drawing on the model. So we got the robot model on the screen. Okay, then we'd like to add some other interesting things. Let's go back to gazebo, and we're going to add a cylindrical obstacle. So there are some standard obstacles here on top, but there are a host of others. You'll be surprised. Some people have a lot of time. They got a number of models here. And of course the Turtlebot house you may already have seen. A ball bearing, a bookshelf. Yeah. Okay. So you can create a very complicated world. There is a way of saving the world. So if you spend 30 minutes creating the world, it doesn't mean tomorrow you have to do all that again. You can save the world and give it a name, and tomorrow you can launch the world, whatever it is that you're researching. So I don't want that, so I got rid of it. Now over here, if you go to the size button, you can sort of, the robot is so small that I don't want this towering cylinder. So I kind of, symmetrical objects can be sized this way. You can also size it this way. Sometimes gazebo will crash, so I don't use it too much. But I like a shorter cylinder here. So let's go back to ROS. So I want to see. So the Turtlebot 3 has a LiDAR on it. So LiDAR, throws out a laser beam, picks up the return, and it can tell where the obstacle is fairly accurately. This Turtlebot 3 LiDAR is a 360-degree LiDAR with a spacing of 1 degree per ray, so 360 rays. When you have 360 rays, then the question is, where does the 360th ray end? It's not at 0, because it'll be 1 degree short, right? Because 0 has to count as 1. So it'll go from 0 to 359 degrees. Got it? 360 rays, it's not 361 rays. But 361 rays will put the last ray back on top of the first, so that won't make much sense. So 360 rays, you have to remember ray number 1 is actually 0 degrees. Is that okay? Straightforward. And 360 ends up a 1 degree short. That's the only way it can be. Okay, now let's add the laser scan. Now, when you're new, you'll say, oh yeah, okay, I added it and everything's fine. No, you have to subscribe to the topic. See, it's empty by default. There's only one topic, which is /scan. So you add that. Is that okay? So this is subscribing to the same topic. It's not a different topic. The LiDAR scan is called /scan, the topic. And RViz is also forced to subscribe to it. Do you get it? Do you get the structure of ROS? From MATLAB, you can subscribe to the same topic. Everybody can subscribe to it. Anybody who's interested. It's like a bulletin board, right? Anybody who goes by the bulletin board can look at it. Okay, I like to make the size of the dots a little bit bigger. You can already see that it's picked up the cylindrical object. Maybe 3. Now, the reason it's blinking is, I bet you it's the, that display is a little bit older and slower. So it appears to be refreshing, but that's because the display is slower. Is everyone clear? Now, you're wondering, I thought the cylinder was in the first quadrant, but that's because this is not rotated to align. You can do that, right? You can do that. The buttons on the mouse happen to be somewhat different, but you can spin it around so that it looks to have the same alignment as gazebo. Is that okay? Now, you take the trouble of setting this up. You choose ODOM as your fixed frame. You bring the robot model on board, laser scan, the topic, and so on. Do you have to do it each time? You don't. Again, you can save the settings. You can save the settings. Just like gazebo, it's possible to save the settings to give it a special name and recall that. When you launch gazebo, you can launch it with a special which brings in all your settings. So if you spend 15 minutes on setting it up, you don't have to repeat it. Any questions? As you can see, there are a whole lot of other buttons. There are tutorials on RViz. There are tutorials on how to use gazebo. But you know how it is. We just learn enough because we don't want to become experts on gazebo and RViz. There's something else we are hoping to solve. So it is for you to explore. There's also a right panel here, which I've rarely looked at, but it's there. Some interesting stuff. Okay, let's go back to gazebo, and I'm going to switch back to the select so that the arrows go away. So you have all these different axes, right? You have all these different axes. If I bring another obstacle down, it's going to have its own axis. If there are cameras here, there's one camera at least I know. There's the LiDAR, but there's also a camera. So this is actually quite a sophisticated robot. It's a real robot that you can turn on the camera and get subscribed to the topic and do image processing. You can do all of that. But the point I want to make is there are multiple axes. So let's say you have 5 robots and you're looking at a scene. You're in the same area. You're patrolling the grounds. Or maybe you're on your way to battle. Increasingly robots are being co-opted into warfare. Then you'll have all these robots looking at the same scene from different points of view. So if these robots are looking at the same scene from different points of view, then the most important thing is you have to ask each robot which direction are you facing when you're reporting all this data. Because if you don't coordinate this, the location first, which XY position they are, but which direction they are looking at, that is the theta, the third. See, when a robot is moving on a plane, there are three numbers that characterize it: X, Y, and theta. Theta is the heading angle. So right now, the heading angle of this robot is 0 degrees. Because the reference is the world frame's red axis. So these colors are not random. So this is the world frame's red axis, world frame's green axis, and the blue axis is up. So 0, 0, 0, but most important, theta is 0 because you draw a line out from the nose of the robot, it's coincident with the red axis. So that's what the heading is. So XY theta of all the robots need to be known for some kind of coordination. If you are building a map, the map will be all over the place until you find out which direction each robot is looking at. To resolve that, you have something known as TF in ROS1. I don't know, maybe a similar thing in ROS2. Maybe they call it TF2. I've seen that many things get named with an extra 2. So there's a TF, and it handles all the transforms. So one of the topics tomorrow probably will get to coordinate transformations. You'll see that TF, there's a package called TF which deals with all the multiple transformations that are needed for coordination purposes. Not just for mapping, but just to plan things out. Now there is a way of turning on the transforms. I hope I remember it. Pretty complicated, eh? Don't see what's happening there? All the axes have been turned on because it's got wheels, it's got a camera, it's got LiDAR. Now you can zoom in and see that. You don't have to look at it from this distance. You can zoom in and see, and you'll see all the axes. Pretty messy, but imagine if you had 5 robots. And by the way, the obstacles have axes too. The cylinder we dropped also has an axis. Every obstacle is going to have a reference axis. And so, you can see how difficult it is. No human being with a scratch pad and pen can handle the information. So you need software. Okay, now we're going to go to a MATLAB program, the drive and circle program. So let me fire up MATLAB and I'm going to bring it over. Last time I forgot because I don't use mirroring. So I'm going to go through this in detail only because this is the platform for any other program that you create. So you have to understand this because any other program, you're going to take this and modify it. And in the process of modifying it, you're going to copy the common stuff that belongs in every program. So therefore, we're going to go through this program in detail. So look at it as being in parts, not just a collection of lines of code. So I believe I may have explained this on Wednesday, that MATLAB is an interactive programming environment. Any previous program you ran, its variables were going to be stacked here. And so therefore, unless you want to use those variables, if you want a clean start, then this is what you need to do. Clear variables, close all, and CLC. Now this ROS shutdown, remember I told you most robotic programs are interrupted with a Control C because they are typically in forever loops. Keep going around a perimeter of a building, and then you interrupt it when you want to stop the program. So if you do that, ROS core will still be alive, and therefore you put a shutdown at the beginning of it. If it exits normally, then there is a shutdown here to catch that. So right here is the ROS shutdown at the bottom also. So whether you interrupt it or not, whether the program reaches, suppose you say, take this robot to that position avoiding obstacles, then that mission has a chance of finishing. If it's a good program, it will get to the destination. In which case it will exit the while loop and it will use this ROS shutdown. Otherwise, the next time you run the program, this one takes care of it. Now, the IP address is very important. In my case, it doesn't change because I have a static IP and set it up that way. So this may change depending on your installation and setup. If it does, you have to go to the Ubuntu side. I don't know whether, so now you copy the software to your own machine. So if it doesn't work quite the way you thought it should, then you need to do IF config. And that's your IP address right here. So you have to change it in two places. In the MATLAB program certainly, but also in the bash file. So you have to edit the bash file and change it if it's not been set up to automatically pick up the IP. If it's set up to automatically pick up the IP, then you only change it in the MATLAB side. So these things you learn, you know. If something happens that it does not work, you know, let me know. We'll fix it. Okay, back to the MATLAB program. So I'm publishing to this topic. Now, how do I know that? Because you can Google and find out, or go to the ROS.org page, you'll figure out what are the topics for Turtleboard 3. You can't guess because computers are stubborn. They like the names to be exact. This is the message structure and that's the topic name. You can bring in any number of robots. You can bring in a second Turtleboard 3. It has a way of differentiating between multiple copies of the robot. So this is your chosen name. Okay, all of this is out of your hands. You have to use it exactly like it. Here you can choose anything you want. I call it PubBell. And then I also subscribe to odometry and model state. So here is a subscription to ODOM. There you don't need the message structure because, you know, don't ask me why, because initially even this was not needed, but then with the new edition of MATLAB it started to give problems, and finally I figured out with the help of a MATLAB tech rep that, you know, you need to add this. Now, this gazebo model state, I think I mentioned this briefly, but you know, there are two classes, so I'm not sure what I mentioned to whom. Model state is the true position of the robot, the true condition of the robot. It's possible to find out in a simulator only. In a simulator, it knows where exactly the robot is. So even if the tire slipped, the simulator knows where the robot is. Your odometry may say you're somewhere else because of tire slip, but the simulator knows. You cannot know the position of a real robot in the real world. Impossible. No matter what you do, how many times you pray, and the pujas you do, you will not be able to know that. In the real world, you don't know the height of a person exactly. You don't know the age of a person exactly, because when was the person born, right? What is the moment when you say, okay, he's born? Right? It's just approximated. So everything is approximate in the real world. So why is model state useful? So model state is useful because if you're trying out a new technique for localizing the robot, remember the first lecture, remote, I broke down the field of robotics into different sub-areas. Localization is one of them. So localization is very important. You're trying to get accurate localization because for an application like the robot going through a minefield, it becomes very important, right? The accuracy is different from you and me walking down the hallway. So you might be doing a doctoral research on some new method of localization. So how will you compare your method, right? You can always say compare it with GPS. In fact, that's the only thing you can do with the real robot. With the real robot, you don't have model state. But if you're doing a simulation test of your algorithm, you know what is perfection. Model state is perfection. It's available to you to compare. And then you can say, okay, my method is good, but it's not that good, you know, let me make it a little bit better. You can never make it repeat model state. Cannot. There's no such, it's not possible. Just like in the real world, there is no perfection. So to deal with the publishing of velocities, I need to create a message structure. So PubBell is used as an example to create an instance of the structure. VEL MSG. And then I set 0.4 and 0.2 as the two velocities, V and omega. I like to use variables that reflect, the nature of that variable rather than give it like single letter names. So I don't use V and omega. I use velocity and rotation rate. And then further down, right here, I push it into the structure. Now, I believe I may have showed you. How did I know this? Well, I'll show you in a second. Once we run it once, you can actually deconstruct VEL MSG into all its fields. And then you'll find that velocity is actually dot linear dot x and angular, the rotation rate is dot angular dot z. Is that okay? So, the radius, I know this from theory, is velocity by rotation rate. The circumference of the circle is 2 pi r. The time to go around the circumference is the circumference by the velocity. Is that okay? Now that's a guess, because the robot is initially stopped, and I'm asking you to go at 0.4 meters per second. So the robot has to accelerate from 0 to 0.4. 0.4 is not its average velocity. 0.4 is not its average velocity. Got it? Can you get into your car and reach an average velocity of 50 kilometers an hour? You can't. So for that purpose, monitoring time is not going to be enough. Monitoring the time taken to go around a circumference is just not going to be enough. That's why this is like an open loop system. In order to go around the loop precisely, well, you can't do 100% precise, you know that, but better precision, you have to monitor distance. We're going to do that in a subsequent program. Right now, we're just monitoring time to get to distance. And the assumption involved in that jump is that velocity is constant. It's not constant. So, I'm getting ready to plot all the footprints of the robot, x, y, theta. Well, I'm not plotting theta, but you can if you want to, x and y. So, I receive sub-ODOM. So, everything is packed in this ODOM, right? It's a message structure. It has x, y, and theta somewhere buried in there. I'll show you later when we deconstruct it. So, that is just, getting the ODOM data, but I do the same thing for model state. I'm not using it here, but I use it often, and my students use it. But in this class, maybe you can use it if you want to, but I like to keep it there. That's perfection. Remember, model state is perfection. ODOM is not perfection. And then I unpack through this MATLAB function deal the x and y positions. Again, the question will be, how did you know this? I'll tell you in a second. Once we run it once, I'll unpack ODOM dot 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 dot, and we'll see how I found that out. Okay, so I unpack it. Now, there is no need to use a different variable. You could have used this whole thing here. Every time you want the x, you can use this, but that's not my programming style. I like things to be clear, even at the expense of additional memory. So that's why I put it at ODOM pose 1. I unpacked it and stuck it in ODOM pose 1, ODOM pose 2. And then down here, remember, this variable is going to be overwritten. So therefore, if I want to plot the whole thing after the robot has gone around the circle, I've got to store it somewhere. Otherwise, it will be overwritten with new values of odometry. So I shove it in x and y. And later on, within the loop, I augment x with a new value. Is that clear? ODOM pose 1 and pose 2, or just for each point. If you don't do something with it, save it, it will be replaced by or overwritten by the next value of ODOM. So within the loop, this is the loop, I'm augmenting x with old x plus this. MATLAB doesn't like it, because anytime you augment a variable and make it a longer and longer array, it takes a lot of time. And they suggest you pre-allocate a variable with size enough to cover the entire plot. They say pre-allocated, but I haven't got to that yet. But that's what you should do if you're a good MATLAB programmer. Okay. So, X and Y. We'll get to this later. This program doesn't have it, but maybe I'll tell you what it is even though we haven't addressed it. So you'll notice the turtlebot 3, even when it is stopped, it starts to move slowly and it will swing all the way around. It sometimes happens, sometimes doesn't. You know, sometimes you go for a cup of coffee and you come back and you just launched the empty world and the robot is facing in a different direction. In other cases, you can actually, if you watch it, you can actually watch it turning around. So I call it jitter. So it's a known problem. Turtlebot 3, the people who developed the software, they're from Hong Kong. They know it and they fixed it for the next version. The 22.04 version, it has been fixed. So, we don't want a robot to be pointing away from where it was launched, right? Because you may be interrupted and you may go and do some other things and come back and launch the MATLAB program. Therefore, there are some lines of code available here to reset it to 000. I did not include it in this basic circle program, but all future programs, I'll show you the lines of code. It's not too many, it's maybe maximum 4 or 5 lines of code that are needed to cancel the jitter. We don't want it to be facing backwards. So this is an open loop control system because I'm going to monitor distance. And how did I calculate that? Here it is. I'm going to monitor time to do distance. So TC is C by velocity. Now the ROS rate object, this is important. I think I mentioned it on Wednesday. We don't run loops in real-time systems as fast as your computer can do it. Based on what that loop is doing, maybe it's controlling a mechanical system. So if it's controlling a mechanical system, then there's no point in running it as fast as a modern computer can run it. That's not a good idea. Because there won't be any difference. So if you're telling a robot, drive, but it's a mechanical system with inertia, you're wasting the computer's resources. So if you slow down the loop rate, then it is possible to take that computer time and use it on other nodes. Remember, we have a number of nodes running in ROS, typically, not here. Typically we have a number of nodes running, multiple robots. So we don't want to run each loop the fastest you can based on your computer speed. Particularly when you have a slow computer, you don't want to do that. So this is an attempt, the ROS rate, so here's the reference if you want to go look it up. But you define a loop, a ROS rate object that is going to run the loop at 10 Hertz. 10 Hertz means 10 times a second, which means that the loop is going to be run once every 100 milliseconds. What happens to the remaining time? Well, down at the bottom, you'll see that this wait for R basically burns off the rest of the time. So, if you burn off the rest of the time, then you're saying, okay, the computer's waiting anyway. No, you can actually use that time to do other loops. I don't have any other loops here. So, the ROS rate object will get back to that. RTT is 0, right? Because RTT is a test condition for the while loop. So this loop is running while RTT less than the time to do the circumference. And then I'm updating RTT here. RTT is being updated to the total elapsed time. Maybe we can take a break and then you can solve these problems and then we can continue. So we take a break for 10 minutes and we can solve these software issues and then we'll continue.